Hey there, welcome to Review of the Quadratic Function. This is the first part. We're going to go back and look at some of the things you're supposed to know about the quadratic function. So, what's a quadratic function anyway? Do you remember? I think these things at the top here are examples in everyday life of where the shape of this function is important. And it's that curvy shape. Remember, and we usually think of these as sort of upside down ones, and here we have a bridge. McDonald's sign's got two parabolas, and what's that? A parabola? Do you remember that? That's the name for the shape of the graph, and over here a parabolic reflecting telescope type idea, and they are important applications of the quadratic function. So what is the quadratic function? Well, here's a graph of one down here, concave up we call this, or convex, and this is y equals x squared. Are you starting to remember? The square part gives you that curvy shape. Can you explain that? We'll come back and look at that. And this one here really is the one that's responsible for the name of the graph, or the description of the shape of the graph. This is y equals neg x squared, done on a calculator. Okay, so you should be able to plot these by hand or with technology. This is from the Casio 9860 Plus, and I'll show you how to do that in a minute. But this one, neg x squared, is what's called a concave parabola, or concave down, and we don't always put down, but you can do that. Concave down, the cave is underneath there. Here you are, sitting in your cave. There you are, sitting in a cave there. So concave is the name for that one. And of course, this is the shape that you get when you throw something up. It comes down due to gravity, doesn't it? In a symmetrical way. And so when the Greeks were playing around with curves like this, they said, gee, that's like what you get when you throw an object, and that's where parabola came from, the Greek word for thrown. So the shape of the graph is a parabola, not a parabola, a parabola. Say it very quickly, run it all together. So it's based on the upside down one, or the concave one, the name of it all. So let's have a look at how you draw that on a calculator, then come back and let's see if we can understand why it's curvy. Come over here. I've got some little calculators here. 9860 Plus. What do? Turn the dude on, get this screen, scroll with this key to graph mode, then enter with the keyboard y equals x squared and hit execute. Then you need to hit shift and in here F3 to get view window. So you're going to specify what size or part of the x and y axes you're going to view the window. Okay, so I'm going to suggest you choose initial by hitting F1. And initial are these conditions from neg 6.3, 6.3, don't worry about the scale, and neg 3.1, 3.1 for y. So if you do that, come back over here. So if you do that, you get this on your screen. So just reminding you, you can draw all the graphs you like with the calculator now. Okay, let's answer the question. Here, if you take x squared, what makes it that curvy shape? Because that's the shape from up the top here that we're very interested in, isn't it? The use of this particular shape in many ways, in a practical sense, in our world. Why is it curvy? Why do you need a square? Oh, this is where we're starting to get the quadratic function. Okay, the quadratic function. And let's have a look. Well, if it was a straight line, let's say a straight line like this, what's true about a straight line? Every time you increase in x by a certain amount, you get the same increase in y. Okay, that's what keeps it straight. That's y equals mx plus c, where m is the slope. So every time you increase x by a certain amount, you get one lot more of m. So that's the slope. Y step over x step. Okay. Well, what we've got to do is stop that. We want it to curve up and increase more rapidly. So you can see on the curvy part, as you go from any point to another point, the x step, if you take that same x step, it's an increasing y step each time. And that's due to not just multiplying x by m, adding c, but by squaring it. So the square is responsible for that steep increase. And I don't know, do you know much about this word up here, quadratic? Hey, that sounds like 4. If you're into rowing and you're rowing a quad scull, there are 4 people in that. What's the story about that? Well, you might look at that, you could Google that. It comes from quadratus in the Greek, associated with the Greek language, and it meant a block. And so quadratus was a block, and like square here, and they were looking at the idea of a square end, and to get the area of that end you had to multiply length by breadth. It was x by x was x squared. So that's the association of quadratic, which sounds like something to do with 4 we use in common English, with the square. Quadratus came from the area of the block, which was a square end sort of thing. So that's where we got this x squared from, and they were looking at the area of that and then plotting graphs, okay, and having a look at this shape. And then we've come to all these uses up here for this particular interesting shape. Okay, well, we're not going to do much with the interesting shape. What we're going to do is play with this function and do things down here. We're going to put numbers in front of x squared, things like that, or just play around with x squared a bit for a while. Let's have a look and go and do that now. So I've got some down here, stuff you're supposed to know. So playing with x squared, if I put a number in front, what does it do? Do you remember? So coming over here, let's put a 2 in front. 2x squared is steeper than x squared. See this? Why? Because after you square x, multiply it by 2. So let's do one. Here's x squared is 4, for x is 2. If we double it, it goes to 8. You can see the effect of this number in front here. Okay, try to understand it, get up close and personal with it, because it's easier then. So what about a third x squared? What does that do? Well, when x is 2, y is 4 for y equals x squared. So if you a third it in front here, it'll be down here at 4 over 3, or 1 1/3. So this affects the steepness of the graph. Okay, that's important, and often called, and depends on the textbook, this is called a stretch in the y by a factor of 2 or a third, or a dilation, sometimes called a dilation in the y direction. That's a proper mathematical term. We're not doing much of that in this particular course. What about if you throw a negative in front? Well, we know that goes upside down, because if you put x is 2 in y equals x squared, you get 4. But if you put a negative in front, that'll become neg 4. So this is actually a reflection in the x-axis, by multiplying it by negative in front. Do you get the idea? I guess if you stay with me on this one, it doesn't matter whether you've done it before or not, you'll be able to get it. Okay, but it would be good. It's supposed to be revision, this particular little presentation now. Okay, let's go down and play with x squared a bit more. What about this? What about before we square the x, we take some number away, like that? What does it do? Let's have a look. Okay, well, if we take away 1, it moves it across plus 1. That's interesting, because here's our basic function. x squared. Now before we're squaring it, we're going to take 1 away and then square it. It moves it across, or watch it, plus 1. But that was neg 1 in there. How does that work? And what about x take a here when a is neg 2? Because it would be x take neg 2 or x plus 2 squared. And that moves it negative 2 across to the left there. So in other words, in this form, a is the x translation. So if you have x take 1, it moves it plus 1. It moves it in the opposite direction, if you like, to the sign. A is the x translation, or that is moves opposite to the sign in the bracket. So if it's x plus 2, it'll move neg 2 to the left. Now I want you to try and think about why that might happen. Okay, draw up a table of values and see if you can see what's going on. Okay, anyway, let's go on. Another move we want to make here. Let's keep the square of x and then on the end add a. What would you expect? Well, here's x squared over here, and if you square 2 you get 4 up here, and then if you add 3, oh, that's gone up to 7, because after squaring all I do is add 3 to every value, so they all pop up. They all pop up by 3. Okay, or what if I make the a negative? Take 4. This would go down to 0. This would go down to neg 1. Hang on, what are we doing? Neg 4, neg 3. Well, down to neg 3. So what's it doing? This is the y translation. Moves it up and down the y-axis, following the same sign though. We don't have to reverse the sign. So if it's plus 3 over here, it's going to be moving up 3. If it's take 4, it'll be moving down 4. It's a y translation. Do you remember any of this? Well, if you don't, join in now. You can get it this time round. Let's have a look at some more changes here. Oh, what about this? Putting it all together, isn't it? Here we've got an x translation, putting the two things together, of h, remember, opposite sign, and a adding on to the end of the function, a y translation of plus k. So this would give you the new vertex, wouldn't it? Let's look at it. The vertex would now be hk, or the peak of the function. The peak of the function originally was 0, 0 in y equals x squared. And if I move that hk, that will be my new vertex. So this is sometimes called the vertex form of the quadratic function. Okay, what about this one over here? Let's do it. Here's y equals x squared. See, its vertex was at 0, 0. If I now move it neg 1 and plus 4, the function should become x take h, x take the x translation, so it's x take neg 1 squared plus 4, or x plus 1 squared plus 4. So given a graph, I can come back and get the formula, or given the formula, I should be able to get the graph by reversing this and keeping that as my y translation. Let's expand it. X plus 1 squared. Do you remember a plus b all squared? First 1 squared plus twice the product plus second 1 squared plus a number down the end. It's x squared plus 2x plus 5. So that's what we've got up here. If you put it on the calculator, you would get this graph. But gee, isn't it valuable to be able to put it in this form, this x take h squared plus k form, so that you can work out where that vertex is without technology? You're a budding young mathematician. Let's get into how does this work. Okay, so lots of stuff here. Now don't get too confused now if you've forgotten this stuff. We're going to come back and learn how to package this up from this form down to this form. It's called completing the square, okay, to get the vertex form. And we're going to do that in a later presentation as we review this quadratic function stuff. But at the moment, I do want you to be able to recognise on the graph what's happened and to get the formula, and vice versa. Given the formula, can you recognise what the graph should look like? Last one now before I let you loose on some problems. I know you're getting excited, you want to get into this. And of course, the other thing we want to know, we've just sort of covered that and moves around the place, but we want to know where's it cut the y-axis and where's it cut the x-axis. And of course, if you could put it in the form x take some number, x take a by x take b, if you could factorise it, where's it cut the x-axis? Cuts the x-axis when y is naught. Do you remember why that's so? The x-axis, well, the x-axis is where you start measuring y positive from the origin here and y negative. But on the x-axis, y must be 0, mustn't it? There's actually an origin there of our left and right movement and up and down movement. So on the x-axis, you haven't moved anywhere in y-land, so y is naught. So let's put y equal to naught up here. Hopefully you've done quite a bit of this in previous studies. There we go. And how can a product be 0? A product of two terms. Hey, this is a null factor law. Null factor law. And nothing to do with rugby, mate, or gridiron, or wherever NFL is, but there you are. Null factor law says, if a product of factors is 0, one of them must be null. So either this must be nothing, or null, or this must be nothing. So we've got one of those two. So x is A, or x is B. So over here, we would say one has got the value A, and the other's got the value B, if you like. Okay, do you remember that? Trying to find where the function cuts the x-axis. What about where it cuts the y-axis? Well, it's the same idea, isn't it? Along the y-axis there's been no x movement. You haven't started moving positively or negatively in the x direction. So x is 0. So let's put x is 0 in the function. Be 0 take A, or 0 take B, and that would come to A by B. So if you like, this is very theoretical now, this is 0 AB. We're not going to do much of that in this course. We're going to use actual numbers, so I think you'll be happy about that. But you remember any of this stuff? We're trying to nail the graph of the quadratic function. We want all the things that it's doing. We want its vertex, want the y-intercept, and where it cuts the x-axis. So we've got a good picture of what's going on here. Just remember one other thing now. You can get the vertex from this form as well, because the vertex here and the axis of symmetry, because the vertex is what? Here's a vertex. It's halfway between the x-intercepts, isn't it? Because we've got symmetry in the graph. So the vertex would be here, halfway between two values, the mean of them, a plus b on 2. And we could find the x value halfway between and then sub it into our original function to find the y value. So the vertex can be found from this form by going halfway between the two x values. That's what we're going to do in a minute, finding that axis of symmetry and then subbing it into the original function and find the y value. Let's do some now. Okay, you might want to go back over the presentation, particularly if you haven't done much of this before, and just get the idea, and then we're going to go on. I'm going to show you how to do all the problems, though, as if you've done nothing before. Okay, so let's go on. First of all, before we do that, let's summarise what we've done. And you might like to take a copy of this. It would be good to put it on your own piece of paper or electronic format, but by writing it in yourself, rather than cut and paste. Because I think it's valuable to actually write this stuff out. It reinforces it in your mind. So the shape of the graph. A quadratic equation with a positive coefficient of x squared. It's concave up. Sometimes called convex, this one. where the cave is up. Quadratic equation with a negative in front of x squared. So this is y equals x squared, or some positive. This is y equals neg x squared. And this is called concave. Don't usually use positive and negative parabola as such, because the parabola itself might not all be above the x-axis and positive. So you're getting a little bit of confusion there with positive and negative use. So this is convex or concave up. Okay, this is concave or concave down, because here you are sitting in, put you in a cave here, mate. No, I loved it. There you are, you're sitting in a cave there. Okay, so got that? Okay, the y-intercept, what do? Is where the graph cuts the y-axis, and so x is 0, hasn't gone anywhere either left or right, and you substitute x is 0 into the equation. There's always a y-intercept for these dudes. Alright, what about the x-intercept? You put the function equal to 0, crosses the x-axis, so y is 0. Sometimes there aren't any x-intercepts. Look at this. The whole function's above the x-axis. Sometimes there's only one, sometimes there's two. So that's summarised down here. You put the quadratic expression, the squared expression, remember quadratus, to 0, and you try to find one of these three situations. We're going to practice that. And of course that's called factorisation. We're going to be doing a bit more of that in the next presentation. Factorisation. Okay, because we make a product of factors, and then you know why we do this. Why do you, when you have an equation equal to 0, try to factorise? Null factor law, null factor law. If you have two factors, product of them is 0, then one of them must be itself 0. That's our entree into solving that type of equation. Okay, the turning point, sometimes called the turning point, quite more often called the vertex or the peak of the parabola. You've got to get that square form. Okay, like that. Or, I have mentioned, you can get the x-coordinate because it's halfway between the two x-intercepts. So you find halfway, and get that x value, and then substitute it into the quadratic equation. This is a nice summary coming from a textbook published by Pearson's. So this is a nice one. When a graph has only one x-intercept, the turning point is the x-intercept. So it's sitting right on the x-axis there. And we call this line, and I've drawn it in there, the axis of symmetry. And it's got an equation, x equals, because it's parallel to the y-axis, it's got an equation x equals a constant. X equals the x value of the vertex. Okay, now we can do a lot with this. It is practice time now, so think about it. Watch me do a problem, then I want you to do some. Okay, these problems come from the textbook Hayes and Harris. We're going to be working with that in this course. Okay, so the first thing is if we're given this doofy here. So notice it's like I was doing before. X take alpha, x take beta. So it's been factorised. It has a number out the front. So it's got a change in steepness, if you like, or it's a stretch or a dilation in the y direction. What we're going to do is try and do everything about it. X-intercepts, the axis of symmetry, coordinates of the vertex, and the y-intercept. Let's go. Let's do this one. So the first thing, let's do the x-intercepts. So we put this function equal to 0. They've left the steps out. When is a product equal to 0? By the null factor law, either the first bracket 0 or the second bracket 0. So I'll just put it in here more fully. X plus 1 is 0 implies x equals neg 1. X take 3 is 0 implies x is 3. They've gone straight through it here, neg 1 and 3. Okay, the axis of symmetry is halfway between that. So let's draw it. Going through it, neg 1 and 3. They're saying it's going to be symmetrical. So halfway between it, what's halfway between two numbers is the mean. Neg 1 plus 3 on 2. So this is the axis of symmetry. Neg 1 plus 3 is 2 on 2 or 1. Remember, halfway between two values on any number line is their mean or their average there. The mean is halfway between the two. Okay. So we've got the axis of symmetry. Now if we want to find the vertex down here, we've got the x value. How do you get the y value in any function? You substitute into the equation, into the y equals equation, because that's what an equation is, isn't it? Do you remember that? The y equals, come back up here, the y equals expression is the rule that all y's must obey so that they form the particular shape, in this case a quadratic or a parabolic shape. So here we put the x values in here and find out what the y must be to be consistent with the other points on this particular shape. So here we are, they're doing it down here. There's the 2 out the front. X plus 1 is 2 and x take 3 is negative. Substituting it in there. Okay, so we've got the vertex. Now what's left? The y-intercept. This is the easy one. Putting x equals 0 in the original equation. So it's 2 lots of 0 plus 1 is 1. And up here, 0 take 3 is negative 3, negative 6. So we've done it all. There it is there. The y-intercept at negative 6. And you can check it with technology, but I want you to be able to do it yourself. Get the idea. Just go back over that perhaps. Let's do the other one. This is negative 2x by x plus 2. So here, what are the x-intercepts? Put x is equal to 0, get 0. But x plus 2 equal to 0, you get negative 2. By the null factor law, if a product is 0 and one of the factors is null. Okay, so now what have we got so far? We've got negative 2 and 0, which is right on the y-axis there. So what is the axis of symmetry? Halfway between the two is x is negative 1. Take negative 1 and sub it into the x pieces in there, and you get y is 2. So we've got our vertex nicely. And then putting x is 0 into the function. Okay, back in the x holes up there again, we've got 0. So that's doubling up with the x-intercept. It's going through the origin, so the x and y-intercepts are that point, 0, 0. Do you get it? Want to do some? Well, what I'm going to do now is show you some problems. I want you to pause the presentation and then look at the answers as you do the problems. Don't do them all and forget to check your answers. So I want you to do most of these just quickly now. So you do one, and then down below, once I've scrolled through this, you can scroll forward quickly and check your answers. These are all from the Hayes and Hayes textbook, exercise 1A1, starting right at the beginning with some revision. So we want you to do everything and use technology to check your answers. Okay, so pause the presentation, have a go, and then I'll scroll down to this question too, and then I'll show you the answers. The answers are coming up down the bottom there. Okay, you pause, and as you do a problem, go and check it. Okay, let's look at the answers now. Okay, question 1, A to C. Let's look at D, E and F. Okay, and then coming on to question 2, matching up the graph with the particular function. So you need to look around and see if you can detect that. Okay, let's go down to the next little example, and that's to do with when you got this form. It hasn't been expanded, it's in the squared form. Okay, and we want to do the same sorts of things without expanding the function. Let's have a look at those now. Here it is. So it's got a steepness change. It's also concave down, if you like, and it's been moved, hasn't it? Try to get used to that idea now. So where's the new axis of symmetry? Let's look at the x movement, x take 2. It's a move of +2, remember, the opposite. What is the vertex? Well, the move is 2, neg 1, so we can go straight to it. Just remembering now, putting this all together, if we have this much, oops, not V, it's a vertex form, let's call it Y, the vertex can be read straight off as HK, because we know this is the X translation and that's the Y translation. The vertex starts off, Y equals X squared at 0, 0, and it's then moved HK under our translation idea. Now, what do we want to do now? We want to find the y-intercept, so put x is 0 in all the x parts of the function, so it's neg 2, x take 2, 0 take 2 squared, take 1 is neg 9. Okay, so the y-intercept is neg 9. So we're down here at neg 9, and the vertex is 2, neg 1, and we've got the axis of symmetry in there as well. There are no x-intercepts here. Let's look at this one. This has been stretched by a factor of a half, or dilated, so it's not as steep as x squared. Okay, this one should have been drawn because it's a neg 2 out the front, etc. This should have been steeper downwards than y equals x squared. Okay, and this one should be less steep. They look pretty much the same, but that's what we should try to incorporate that. What's the axis of symmetry? Well, where have things been moved in x land? Opposite sign to that, so it's a move across of neg 3 naught. So here, y-axis x squared is steeper. That's our parent. That's where we started. Vertex naught naught. X plus 3 moves across neg 3. There's no other number added, so it's still naught. The axis of symmetry, therefore, is x equals neg 3. And what is the vertex? Well, we can say here it's neg 3 naught. And where's it cut the y-axis when x is naught? So put x is naught in here. Got a half of 9, which is 4.5. So it goes up there. So this is another form of the quadratic function that you could work with. Right, time for you to have a go. So come down and want you to do the same thing with these functions. Let's see if we can get them all on there. Okay, we're not quite, we have missed the question now. Right, so state the equation of the axis of symmetry for each of these, the coordinates of the vertex, y-intercept, sketch the graph, and use technology to have a look. Okay, you're not meant to try and accurately accommodate these numbers. Just try to make it a steeper graph there than x squared, or here, yes, a steeper one, or here a less steep one than x squared. So try to accommodate that, but you're not meant to be doing it accurately at this stage. Okay, mind you, technology will give you the accurate one. Alright, so have a go. Remember, I've got the solutions coming up down below, so have a go at one part A, then scroll the screen forward or the video forward and mark that one, then come back and do the next one. Mark them as you go. Now we want to match each quadratic function with its corresponding graph. Can you spot what the changes here would do to the function? So 2 part A, what graph does it match up with? A, B, C, D, E, or F? Let's have a look and see if you can do that. Let's see if we can get them all on here. Yep, GHI. So each of these functions up here matches with one of these graphs. Okay, be careful as you go. You're trying to work out what the vertex is, because this is in vertex form up here. So if you could work out roughly what these vertices are, then I could think you've got the idea of matching it with the function, because the function is in vertex form here. So that will be your key in to this function, or to this question. Okay, pause it, have a go. I'm going to show you the answers now. Okay, 1A, B, can't quite see C. Do C and D. E and F and part 2, they're all there. So that's it for part 1. There's a few more parts coming up to review the quadratic function, important function. Okay, but for now, it's cheers from me. Catch you in another presentation.